Okay, so our task is to find the potential and electric field in more complicated situations now than what we've been doing before. And I will start with the last slide of the previous lecture, of the lecture on Wednesday, the 26th. Okay, and you remember that I was talking about the uniqueness theorem. Um, oh, this one looks a bit dead. So I was talking about the uniqueness theorem, and the point that I'd made was that if the potential, now this line is not, I did not write it down in my notes on the 26th in class, but it is now in the lecture that's posted. So the point was that if the potential is specified on the surface, this boundary that encloses a certain volume, so if the potential is specified on that boundary, then the potential in the enclosed volume is uniquely determined. That's what the uniqueness theorem says. I'm not proving it, I'll just use it. Okay. Um, and so all I have to do is guess, just find a way of finding the simplest uh, form of the potential inside this volume that recreates this potential that is given to me on the surface, that respects the potential on the boundary surface. And then whatever form I have guessed is the solution because it's unique. Okay, so let's start. Uh, the first method is called the method of images, which works in certain situations. It works usually if you have a point charge involved, okay, and this point charge is brought near some kind of um, conducting plane or sphere or things like that. And then the question that is asked is that, well, can you tell us what's the potential in the region where the charge is? That's one question. And then what might be the force of attraction between the conducting plane or sphere and this charge, and how much work is stored, how much energy is stored in this configuration, things like that. And so in certain select situations like that, uh, method of images works just fine. And if it works, it's really simple. It does involve some guesswork. So it's not always, I mean, unless someone does this for a living, it's not always um, easy. But there are some easy situations, and the trick is to just remember these easy situations and apply them. Just apply them as is to some related, similar looking situations. All right. And if you don't get success, then you move on to other methods. But anyway, so method of images, and it's good to know these. Whenever you take a advanced course, like in grad school or something, they will just assume you know these. So we have to do them. All right. And so let's consider the problem of a point charge plus Q, let's say, okay, held a distance um, d above an infinite, and remember that just means that the distance d is really small compared to the extent uh, of this infinite thing that I'm talking about, infinite grounded conducting plane. So d is really small, so small that you don't notice the edges of the plane. And then the question that's asked is that what is the potential in the region above the plane? And this is just a solved example in the book. So, like I said, I really like the book, and you can read that as well. All right. I'm just following it quite closely. Okay, so let's do this example. Let's say that let's make a drawing. So here's the Z, and here's the Y axis. There's X. Okay. And the plane, um, we'll draw that in. The plane looks like, here are the kind of edges. It's infinite really, but okay, that's what the plane looks like. And there is a charge located a distance d from the center, d from the plane, I mean, right? And so now this q, so this is a infinite grounded conducting plane, right? So the q obviously is going to induce, if it's positive, it induces some negative charges on this plane. Okay. Um, all right, and and the Q holds them there. Okay, they're not able to just flow away to the ground. Okay, so how do I approach this? Well, remember now, I need to find, I've been asked to find the potential in the region above, in the region above the plane. So, in the region that is in the region where Q lies, right? So above the plane. So what I'll do is first, remember I said that the potential in the region, in this region, should satisfy the boundary conditions. So let me write down the boundary conditions first. Okay, so the all important boundary conditions. The first boundary condition is that the conducting plane is grounded, right? So because the conducting plane is grounded, the potential must be zero on the plane, right? And this plane, of course, lies in the xy plane, right? Let me make that clear. The grounded conducting plane lying in the xy plane. Okay, so that means that z is equal to zero. So that's your first boundary condition, that the potential is zero at z equals zero. And the next boundary condition is that far away from Q, so above the plane and far away from Q, um, as you know, far away from Q, the potential must go to zero, right? When the at far away locations near infinity, V must go to zero. Okay, so those are my boundary conditions. And what we need to do is we need to solve Poisson's equation. Remember Poisson's equation? That's Poisson's equation from the last lecture. And if in regions of charge-free space, the right-hand side becomes zero and you have Laplace, Laplace's equation. But here there is a charge, Q, right? So we have to solve Poisson's equation. Poisson's equation. Uh, and of course, subject to the boundary conditions above. That's all. That's what our task is. Okay, so the first thing I'm going to do is actually, as the book says, just solve a completely different problem. Meaning, I'm not going to think of the grounded plane as such. I realize that the Q is inducing some negative charge on this plane. So now this is where the guesswork starts. What I'm going to say is that I notice, I mean, from experience, others have noticed, and now they're sharing their knowledge with us, that note that if we replace the grounded plane, okay, by just simply by a charge, because you think that the Q is going to induce an equal and opposite charge, right, on the plane. So how about if I just sort of um, humor this for a moment, that if we replace the grounded plane by a charge minus Q, okay, and it's like an image. So it's, but like located behind a mirror. So located at a negative d distance from the xy plane. So 0, 0 minus d. Okay, it's like a mirror image. And it will become clear why I want it there. Okay, so in just a moment. So let's do this. And then um, okay, so note that if you replace the ground plane by charge minus q located at 0, 0, and minus d, then we find that the potential, okay, so let me just draw what I'm saying just to be clear, that here's y, here's x, here's z, and I've replaced, the problem has become really simple now. All we're doing is we're saying here's q, and it was located at distance d above, so it was at 0, 0, d, right? And all I'm doing is I'm saying consider a charge located at 0, 0 minus d, okay? And if this was q, then this is minus q, okay? And then let's ask for what the potential is at some point above the plane, above the XY plane. So let's say here, okay? So at this point P, well, we know that we have to look at the potential from Q would be, and this would be curly R, right? Let's call it R1. And then from here, this distance is going to be curly R2. Okay, and so the potential we know is going to be from a point, from these point charges at the point P, is going to be Q divided by R1 minus Q divided by R2. It's just the sum of the potentials, right? But I know what R1 and R2 are in terms of, I can write them out in terms of, the different variables here. So let's write that out. So this is going to be 1 over 4 pi epsilon naught. And I can factor out the q, right? And then inside, what's the um, distance r1? Well, I mean, P is located at x, y, and z, right? That's what P's coordinate is. So the distance of x, y, z from 0, 0, d is going to be square root of x squared plus y squared plus z minus d squared, right? And then the distance of xyz from 0, 0 minus d would be square root of x squared plus y squared plus z plus d. Okay. And the boundary condition says that this potential, from 1, that potential must be 0 when z equals 0, okay? And 2 says that v must go to 0, okay? When the point P, is very, very far away from where Q is. So this is much, much larger than D, right? Point P is far away from Q. So those are my boundary conditions. So, well, now if I look at what I wrote down here for this simple situation, I notice that, of course, when z equals 0, then these two cancel out and my potential is 0. So that is satisfied right there. And the other thing is that, yeah, when this becomes much, much larger than D, then the D, you can just neglect. And then once again, the two terms cancel out, okay? For, again, they cancel out and you get the potential goes to 0, okay? So I find that this potential that I wrote here, okay, the V above recreates the boundary conditions, okay? Which means this must be the solution, okay? It recreates the boundary conditions of the original problem. Oop, I wonder if you were able to see what I was writing. So it recreates the boundary conditions of the, let me just make sure that it doesn't happen again. Okay, so this the V that I wrote here recreates the boundary conditions for the original problem. So this is the solution then. Okay, so this is the solution to our problem. Recreates the boundary conditions to the original problem. That means this is the solution to our problem. And now we can answer, now that we know the potential, we can straightforwardly answer some, tough questions. Like question 1 would be, can you, what is the surface charge distribution induced on the grounded plane? So if someone asks for what is the surface charge induced, surface charge means surface charge density, sigma induced on the plane. That's one question that one could ask. Question 2 could be that what is the total induced charge on the plane. Now, this we know, we know that, we assumed, well, we didn't assume anything, we just solved a different problem, but we expect that the total induced charge should be minus Q. But the question is, what is the total induced charge on the plane? We expect the answer to be minus Q. But we should prove it by showing that if I take the integral of sigma over the entire area of the plane, okay, sigma dA integrated over the plane equals negative q. Okay, so, and this is part of your homework for a certain problem related to this. And then there's also, some other questions. For example, someone could also ask that, and these are, questions that unless you did it by this method, they would be hard to find the answer for. So other questions are, um, and I should number my pages. So I'll get to numbering them later. All right. Another other questions are that what is the force of attraction between Q and the plane? And then another question is that what's the energy stored in the system? All these are good questions, but now they're very straightforward to answer from what we um, from our new problem. Because, for example, I mean, let's do the easiest one first. Okay, so let's do the force of attraction. Okay, well, we said that um, there's my potential. Okay, and so the and I replaced it by this other model that is modeling the conducting plane for me. So the force of attraction is simply that between the charge Q and its mirror image. Force of attraction between Q and its mirror image, okay, is, and that's easy, right? It's just Coulomb's law. Q and minus Q divided by the distance between the two, which is 2d, right? Because this also is a distance d below, right? So 2d squared. Isn't that simple? Isn't that cool? And so this answer is, it's an attractive force. And we're done. So that was really easy. One might also say, well, what about the energy stored in the system? And this is the only place where one has to be a little careful. The energy stored, you would say, is the work done, right? And so let's say that I bring in the charge Q, uh, you know, let's say I bring in both these charges, Q and negative Q, and bring them in. So let's start with the minus Q wherever it is. I brought that in, and now I'm bringing in Q from infinity, right? And so the work done would just be what the potential of the negative Q is, where the location of, at the final location where I brought Q. And so that would be 1 over 4 pi epsilon naught, and the potential of the negative charge Q at the location of positive Q is simply negative Q over 2d. And so the work done per unit charge, work done in bringing a unit charge to the location where Q is that. And now I just have to multiply it by the charge that was brought itself, and that would be the work done. So I might say that, this is equal to negative Q squared over 4 pi epsilon naught 2d. But I have to be careful because and this is the one place where it's only when you look at the energy stored that you have to be careful, because it's not really that you brought in two charges. What you did is you brought in the positive Q. It created a negative, like it created this negative charge, right? And as you're bringing in Q, the negative charge, uh, when you were looking at this problem, you were bringing in both the charges, and they were constantly sort of, um, the work was being done in moving, both of these charges toward each other and then holding them at that distance. But in this case, the negative Q was always on a conducting plane, and so no work was involved in it moving around. And so it turns out, and this is the one place that you have to be careful, that the work done is actually half of this. Okay, because it's not like we were bringing in two charges from infinity toward each other. It's because, one of the charges is actually on a conducting plane. It's not really located at a distance minus d down below the xy plane. So one charge is actually on a conducting plane, and this charge uh, moves around, um, moves around on the conducting plane without costing any energy. So no work is done and it's moving around. So it's really just the positive Q, and you divide this by 1/2. Okay, so this is one difference, but otherwise, everything else that we are going to talk about, you can just think of the 2-point charges. All right, so I should make this, so this goes to that. Okay, so all right, and you can read the book for further explanations, more detailed explanations. I'll just keep moving on. Now let's look at answer one. So what is the surface charge sigma induced on the conducting plane? And you recall that um, from boundary conditions. Okay, see, I know what the potential is. It's written out here, right? And so all I have to do is apply this boundary condition. Okay, I know the potential at the surface. So I'm just going to apply this. Okay, so let me write that down. Uh, the potential, and so V2 means here, V2 means that this is, above the plane divided by the normal to the um, normal to the xy plane, right? Normal to the surface. I'll get to it in just a sec. So this is, and this has to be at z equals 0, right? So it's at z equals 0, and really the normal direction here just means d by dz, right? Or let me make that point in the next. Okay, and then minus the potential, and what's the other side? Well, there is no other side. It's on the plane. Okay, so this is on the plane itself, and this is also normal to the plane, and this is at z equals 0, right? So I'm just writing out this relation here, and this is equal to minus sigma divided by epsilon naught, and my task is to find this. Okay, so that's a very useful relation, this boundary condition here. Okay, so let me remove that, and go back to calculating this. All right, so in our case, sigma, which is what I'm after, is equal to, let me take the minus epsilon naught over to the other side. And this then becomes just dv by dz, because the normal, as you can see, the normal to the conducting plane is in the z direction, right? That's the change, the potential changes in that direction. That's what I'm interested in. And so this would be at z equals 0. And the potential on the plane itself, it's a conducting plane and it's grounded, right? So this is just 0 on the conducting plane, v equals 0 everywhere. Okay, all right. So then that means that I'm just left with this, and that's all I need to look at. So I have the potential written down here, and you can easily calculate the derivative minus epsilon naught. I see a constant q divided by 4 pi epsilon naught. And then I just need to take the derivative with respect to z of this. And you know how to do that. You first take the derivative of that. So this is all this to the power minus half. So I would get a minus half, and then 1 upon x squared plus y squared plus z minus d squared, and to the power 3 over 2. And then you have to go inside the argument and take the derivative there with respect to z. So you get that. Same on the other side. So first negative, and then I get another negative. It's the same as this, except replace the minus d with a plus d, right? So okay. And of course, this has to be evaluated at z equals 0. So if I put in z equals 0, what do I find? Well, here epsilon naught goes away. I have a q over 4 pi. This minus sign and this minus sign and that minus sign, they'll all cancel. This minus sign, this minus sign, and let's take this minus sign, right? So actually, there, 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 they will all cancel. So I am left with q over 4 pi, and here the z equals 0, right? And by the way, these 2's cancel. So minus signs have gone away. I'm left with a minus d over x squared plus y squared plus z is 0. So d squared, 3 halves. And I have from here, there's a minus sign, and I get another d. And the denominator is going to be the same. Okay, so that means that sigma, therefore, is a function of x and y. It has an xy dependence, and it's equal to minus, this is a 2d, right? And so 2d, the 2 with the 4, well, let me just write it out. So minus 2qd divided by 4 pi x squared plus y squared plus d squared 3 by 2. Okay, and so this is equation 310 in the book. And there's your surface charge density. It's a function of x and y. Okay, and of course it depends on d. And as expected, the induced charge has a negative sign, right? Has opposite sign. to Q. Um, and as expected, the has opposites and attains its maximum value. Where does it attain its maximum value? When you're closest to the conducting plane. So its greatest value, its maximum value at um, well, what I meant was it attains its maximum value where the charge is closest to the plane. So at x equals y equals 0. Okay, the closest um, separation of q from the plane. Okay, so all that makes sense for fixed d, x equals y equals 0 gives you the closest separation of the charge from the plane. Finally, answer 2, I already discussed here that, you expect the answer to be negative q, but we should prove it by integrating this over the plane. Okay, so, and proving that it's minus q. And for that, you can look at the book. Okay, look at book. In fact, say what is the um, that's equation 311. Okay, and you can see how that's done. All right. So that's the method of images. Now, you can have a more complicated situation than this, and these are the only two situations that we will study, and then hopefully be able to apply them to the homework problems, just sort of by modifying them just a little bit. Now, here's an example of where, you know, it's a lot more complicated. Like it may not have been easy to just guess. I mean, like the previous one, it was kind of okay. You take a Hail Mary and like, yeah, I feel I'll see a mirror image in this conducting plane and let me solve this problem. And oh boy, it actually works out. But sometimes, the situation can be more difficult, and this is uh, solved example 3.2 in the book. All right. So once again, I mean, you read the notes and you listen to my um, comments here, and then it should all make sense, hopefully. Okay. So in this case, what we're going to do is we have a sphere, okay, a grounded conducting sphere, right? So this is a grounded shape is now different. So what's different about this problem is that now we have not a plane, but a sphere, okay? And there is a charge, okay, q, positive q, located a distance a from the center, all right, and this sphere has radius r. So the q is obviously going to, again, induce a negative charge on this conducting sphere, right? Um, and so there will be some charge sort of induced on this, okay? And what we have to do is find the potential outside the sphere. So in this case, find the potential outside the sphere when this charge is brought near this grounded conducting sphere. Okay, and in this case, the radius is r and it's less than a. Okay, so what we do in this case is that let's first write down the boundary conditions, right? So uh, well, I mean, we start off with in electrostatic situations. The surface of the conductor is an equipotential. This is what we used in the previous problem also, is equipotential. And, it's grounded in this case. So V equals 0 everywhere on the sphere. Okay. And so once again, I'm going to replace the problem. I'm going to try what we did last time. Okay. So what we're going to do is we're going to take this sphere and there's Q, there's the origin, there's R. But what we're going to do is we're going to replace the sphere with a charge Q prime, okay, with a image charge Q prime, okay. So replace sphere with image charge Q prime placed a certain distance, let's say B, away from the center. Okay. So, oh, and by the way, what did we have? We should have another boundary condition that the potential is for far away from the charge, right? So, um, so that should also, we should let that happen. Um, okay, so let's write out. Okay, I took a drinks break quickly, and you'll notice that I've actually erased in the restatement of this problem where I am replacing the conducting sphere by just this image charge, Q prime. Okay. So now I'm not showing the sphere anymore because I've replaced the problem. I'm only solving the problem of these two charges that are separated by um, this distance. I mean this distance here is still a. Okay. And that's why I redrew this. Okay, and so now the boundary conditions are V equals 0 everywhere on the sphere. And then, so this is the first boundary condition. And the second boundary condition, as usual, is that V should go to 0 as, um, the um, distance of the point. Like, let's say we're finding the V outside the sphere, let's say here at this point P, right? So this point P, let's say, is located a certain distance, curly R. Actually, in this case, that would not be curly R, that's the origin. So that's just distance R. Okay, so as R becomes much, much larger than A, then the potential should go to 0. That's the usual boundary condition. Okay, so let's just write out now what the potential at this point P, okay, is from these 2 point charges. Okay, and so let's also put in this R location. All right, so what do we have this charge, which is located at a distance r prime, let's say for q prime, right? So let's call this r prime. And this charge q is located at a distance curly r, okay? And let's say that this angle here is theta. Okay, so P, it is r and theta, okay? And there's azimuthal symmetry in this problem clearly, so I'm only focusing on r and theta. Okay, so because it's a sphere. Okay, so this is a very simple problem to solve. I can just write out what the potential at P is. It is simply Q divided by 4 pi epsilon naught R. That's the potential from plus Q. And the potential from the Q prime is 4 pi over epsilon naught R prime, right? That's it. And so let me write it out a bit more. So this would be Q divided by 4 pi epsilon naught. And what is curly R? Well, using the cosine rule, I can write this as curly R. So there's R, there's A, and the angle between the two is theta. So I just get R squared plus A squared minus 2AR cosine theta. Okay, and Q prime, and this is simple also. Now it's this skinny triangle here, and this would be R squared plus B squared minus 2BR cosine theta. All right, so I've got these two expressions. And now the question that I have to ask myself. So first, let me just make one simplification here. Let's rewrite Q prime as, uh, some fraction of Q. And you do, it's the image charge. So and this is a grounded sphere. So you do expect the Q prime to have a negative sign. So let's put this negative in there. Okay, so now my task is to choose. This is where the guessing happens. And you'd see that it's not easy. So that's why this is an example of, like, anytime you have a sphere and you have an image and you have a charge near it, then you think of this guess that was made and sort of try and either modify it slightly in some obvious way or work with this guess. Okay, so but anyway, let me first write down what what I have to do is choose F. Okay, here basically choose the size of Q prime, and then B, which is the distance, choose F and B, distance from the origin, such that V r theta is equal to 0 at little r equals capital R, right? Where the surface of the sphere is. So you see how the radial coordinate really works. Everywhere, wherever little r is capital R, I want this potential to go to 0. Okay, so how to do that? Well, um, it turns out, this is where an inspired guess happens, that if you choose, let's choose F equal to uh, R divided by A, and little b equals R squared divided by A. if we make this choice, then something pretty miraculous happens. Okay, so this is for the second term. So let's, what happens. The second term becomes, um, minus uh, r divided by a times q divided by 4 pi epsilon naught square root um, r squared plus, now b squared is r to the fourth over a squared minus 2b, which is r squared over a, and then r cosine theta. Okay, it becomes this, and as little r, and when little r equals r, this term becomes something pretty miraculous happens. Okay, so now little r is capital R. I have an r squared, r fourth over a squared minus 2r cube over a cosine theta, which now you realize that if I were to uh, factor out uh, I see there's an r everywhere. So let me factor out an r, which means taking out an r squared from inside. And then let me also factor out an a. I'm trying to make this term look like the first term, and that by all this factoring. And so if I take this out, factor this out, I can cancel the two, and then I'll just have a q at the top, just like on the first term. But something miraculous is about to happen. And what happens is that this guy, the r squared goes out, but the divided by a, so I need to have an a squared for the first term. From the second, I took a r squared out of this there, so this becomes an r squared. Okay, and I took an a out, and that's fine. The a squared got factored out. And then I have a minus 2. Took an r squared out from here, so I have just the r. And I took an a squared out, so I need to multiply this by a cosine theta. Now this, of course, cancels with that. And what you notice is that what I have left here, now is that the second term, well, let me actually at this point write out what v r theta is at r equals r. So the first term is, therefore, first term is q divided by 4 pi epsilon naught square root, little r becomes capital R. Okay, and the second term from just above, from here, is a minus q divided by 4 pi epsilon naught. And I have a squared plus r squared minus 2ra cosine theta. And voila, this is equal to 0. I have satisfied the boundary condition. Okay, so this was where the inspired guessing happened. And you see what it did. So if you have to solve a similar problem, then keep this guess in mind and work off it. Okay. So there is such a problem in the homework, and hopefully it'll sort of clue you in on how to use this method. And obviously the potential as R becomes much, much greater than A, right? Then you can neglect the A terms. and you're just left with a q over 4 pi epsilon naught r, right? In the denominator, same from here. And so the potential will go to zero as r becomes, because they're both depending on 1 over r. So, it all goes to zero. Both the boundary conditions are satisfied, and the answer is that the potential at r and theta is, here's your first term, and your second term is minus r over a q, and I wrote it out here somewhere. There it is. 4 pi epsilon naught square root, it's right here, r squared plus r4 divided by a squared minus 2 r squared over a little r cosine theta. So that's your potential. Okay, and so that's your potential right there. So that's the answer. And at this point, I'm done with talking about the method of images. It works in very limited situations. In fact, these are the only two situations that I've ever sort of really used them in. In my graduate class, I think there was one other way in which I think there were like a succession of images that one could write down. It was for a problem in the book Jackson, the famous Jackson book that's used for the PhD courses. But really, these two problems should take you as far as the method of images will go, and the homework will get you some more practice with this. Okay, so you should be set for the first 3 or 4 problems on the homework. Okay, now I will be talking to you soon again. There's one other lecture that I want to record. Okay, talk to you soon. Bye.